All right, going to get into some problems that are more like what you'll see on Hawks. So let's do it. Got 4 problems here. It's going to be a long video, but probably only going to be 2 or 3. Well, it doesn't matter how many videos there are. We got to get through the material. So a manufacturer of potato chips would like to know whether its bag filling machine works correctly. At the 283.5 gram setting, is believed that the machine is underfilling the bags. A 40 bag sample has a mean of 278 with a variance. Oh, wow. Okay, guys, variance. That show. We don't need the variance. We need the standard deviation. So remember, the standard deviation from many moons ago is the square root of the variance. So guys, we got to take the square root of 400 before we get into this problem doing anything too wacky. So the standard deviation turns out to be 20, which is what we're going to need, and not the variance. Right? The variance is fine. The variance is in fact a better measurement of spread in many ways than the standard deviation. But this process of test hypotheses refers to the standard deviation, not the variance. All right, so level of significance is 0.05. That's my alpha. Population distribution is normally distributed. That's not a big deal as long as we're above 30. But if we had only 12 bags, we would need to know that. So if we had less than 30, we would need to know that. But since we got a sample size of 40, I think we're okay. So null and alternative hypothesis. Go to your alternative hypothesis first. This is clearly a mean problem. Doug. And what are we testing here? Under filling the bags. Supposed to have 283.5 grams. Are we underfilling that? And again, don't do stupid statistics. Somebody that knows squat nothing about anything about statistics will say, well, it's 278. 278 is less than 283. Done deal. You don't need that fancy schmancy statistics Darbo's teaching you. Yes, you do. That 278 is specific to those 40 bags. Those 40 bags aren't all that's being created. We have, I would assume it's probably filling 40 bags per minute. We're trying to generalize to a population here. So, guys, notice the number, same number always goes here, same letter goes here. The only thing that changes in these is that. Alpha level, 0.05. Find the test statistic and the p-value. Well, guys, this sets up classic for a t-test. And as long as it allows me to, I'm going to use my calculator for t-test. I don't have my numbers, so I get my statistics. So my mu0 is the 283.5. My sample mean for the 40 bags is 278. My standard deviation is 20. You'll get the wrong answer if you use 400. And the sample size is 40 bags. Testing less than, so find the inequality that matches perfectly and select it and hit calculate. The p-value approach is what? Our p-value from the calculator. This is the test statistic. The test statistic is negative 1.74. The p-value is 0.0449. How does that compare to our alpha? It's less than. So we reject H sub O. There is significant evidence that the potato chip bag filling machine is underfilling its bags. This company is cheating its customers. So there is significant evidence. There is sufficient evidence, which we could say, that the bags are being underfilled. Okay. Determine the decision rule for rejecting the null hypothesis. Okay, that's what we got here. Just like before. Same old, same old. Look at your alternative hypothesis. What's the sign? It says your reject area is going to be down here. How much goes down there? Our alpha. This is a t-test, so degrees of freedom are important. So guys, let's work the problem. We need to find the test statistic here. We know it's going to be t-critical. That serves as a line in the sand. The line in the sand between failing to reject and rejecting. So guys, we need, for this line right here, we need to the left of it 0.05. Degrees of freedom are 39. So negative 1.685. So guys, any test statistic below negative 1.685 we will reject. Let's go back and see where ours was. Well, it's right there. It's still up there, isn't it? Our t-critical was negative 1.74. So our test statistic, I should say. Negative 1.739. Yeah. Guys, that falls right over here. Just barely to the left of the negative 1.685. Falls in the reject region. So is there sufficient evidence to support the claim that the bags are being underfilled? Yep, sure is. Why? Because both methods, using the p-value approach, well, actually I said find the test statistic and p-value. So guys, the p-value here was 0.0449, and the test statistic here was negative 1.739. But I got both of those from my calculator and showed you how we do that. So using both ways, the test statistic p-value approach and the decision rule, we fell in the reject region. So it's not looking good for the manufacturer of that potato chip filling company. Guys, nowhere I think is hypothesis testing as effectively used as in politics. But the problem is nobody in politics understands stuff like this, it seems like, because you see all kinds of wacky results out there. So let's just go through this and see if we can learn anything from this. The mayor of a town has proposed a plan for raising taxes to support education. A political study took a sample of 2,000 voters in a town, found that 28% of those sampled favored raising taxes to support education. Using the data, a political strategist wants to test the claim that the percentage of town residents who favor raising taxes to support education is less than 30%. All right, let's do it. Always start with H sub A. This is a percentage problem. We want to test less than 30%. P less than 0.30. H sub O is always the same letter. The opposite inequality, the same number. Okay? Calculate the test statistic. Well, what are you going to do here? use the calculator. I want to ultimately determine the p-value. I want to ultimately do the test statistic. So guys, what you need to know here is this is a percentage problem, and those are worked by a one-prop z-test. Well, gang, let's do it. All right, gang, what are we doing here? Testing what? 0.30. What's our sample here? What's the x? Well, that's 28% of the 2,000. Now, if this number, let's say this number had turned out to be like 561.2, something like that. I can't do that for x. I'd have to change that to 561 or 562. But we lucked out here because we have our 2,000 times 0.28. That turned out to be on an integer, so 560 is fine. 2,000. And we want to test somewhere less than. Test statistic, there it is right there. Don't have to do any work at all. Negative 1.952. Now, how do I know this isn't a t right here? I didn't do a t-test. T-tests are when we test claims about means. We're testing a claim about a percentage. A percentage always in this class uses a z-test, so the t doesn't even apply here. That's just silly. We don't want anything like that. Determine the p-value of the test. Well, that's a lot of work. There it is right there, 0.0255. That's the p-value. Under the null hypothesis, that's the probability of getting a sample as low or lower than the one that we actually got randomly. Make a decision to reject or fail to reject the null at the 0.05. Our p-value, well, I want to write this out. Is less than our alpha. So what do? We reject that hoe. Sorry. It's been dying to come out. I had a graduate professor that always called it the hoe. So sorry, that shouldn't have come out. But it did, so screw it. All right, so 0.05. Now here's what happens to statistics. Statistics gets a bad rap sometimes because I told you back in a previous video, maybe even this one, that there's other choices for alpha. What if the researcher decided, yeah, I'd rather test at 0.01. Somebody says, well, why? I said, I don't know, I just want to test at 0.01. All right. Well, in that case, the p-value would be higher than 0.01, and we'd fail to reject. The consequences at 0.05 are reject the null and conclude that the percentage of people in this community who favors raising taxes for education purposes is less than 30%. Because we rejected that statement. We're left with this one. But if we had tested at a different alpha level, which is completely legal, then we would have failed to reject. We'd run around here saying that's when we would have accepted this statement. No, it's about 30%, we would conclude. Yeah, that's why you got to be careful with statistics. You got to know what's going on. Because people can manipulate things, and this is one of the easiest ways to manipulate a study, that along with fluctuating sample size and getting too much power and not enough power and different things. But we'll talk about that maybe. I don't know. Depends on how much time we get. Number 3, insurance company is reviewing its current policy rate. It has been led to believe that the average claim amount is $1,800. They are concerned that the true mean is actually higher. That'd be something that insurance companies would care about, right? If the average claim is 1,800, or at least it's believed to be that, but it's actually higher, and they would need to know so they could raise their rates. So assume the company randomly selects 40 claims, calculates a sample mean. Guys, that right there tells you you're going to use a t-test. So if this had been a percentage problem, then you would have used a 1-prop z-test. I'm only requiring you to know 2 of them. There's something else called a z-test, and there's different things. But I'm only requiring you to learn 2. The 1-prop z-test and the t-test, because I'm cutting out the z-test because it's not common, and we're running a little bit short on time. All right, null and alternative. Where do you start? Start with the alternative. Clearly a mean. What are we concerned about here? Reading the problem? It's higher. The null, less than or equal to 800. Find and interpret the values for the appropriate test statistic and the p-value. Boys and girls, I'm going to use my calculator again. I'm going to use a t-test. They're concerned with 1,800. Sample mean for these 40 that they collected is 1960. Again, just because the 1960 is higher than 1,800 tells you absolutely nothing. Go ahead and let the process play out. Create your test statistic. Create your standard deviation, so on and so forth, your p-value. Standard deviation is 500. And it looked like there were 40 claims that were sampled. Our null is greater than, so choose it. And you calculate. Our p-value is this number right here, 0.0249. So again, from our calculator, whoa, we're doing a t-test here, aren't we? So our test statistic is 2.0239. And your p-value is 0.0249. Find and interpret. I'm going to talk it through. Our sample mean is 2.0239 standard errors above the claim in the null hypothesis. The p-value says that if the null hypothesis is true, there is a 0.0249 of getting a sample as large or larger than the one we attained randomly. What's your decision? P-value 0.0249. Alpha 0.05, clearly less. Reject H sub O. Calculate and interpret the 95% confidence interval. Guys, I'm going to use the calculator here. Use the t interval. It was waiting on you. It knew you were coming. So it looks like the confidence interval is 1800.1 up to 2119.9. Granted, this 1800.1 is just a little bit bigger than the cutoff point, but it's kind of like being pregnant. It doesn't matter. It's bigger. All right. It's not kind of pregnant. This is, I mean, an inch or a mile. 1800.1 is bigger than 1800. All right. I think this is a really interesting problem. I'm glad I forgot about that. I included this, but I was in San Francisco a few years ago, and I found it to be an extremely liberal town. Uh, some of it I liked, some of it I didn't, but that's just the way I am politically on about everything. He gave me 15, 20 questions to determine whether I was extremely liberal or extremely conservative. I'd answer about 10 and 10 each, so I'm really kind of split down the middle on stuff. Uh, I'm not going to let a political party think for me. Too damn stubborn for that. Uh, but anyway, this is something that I heard about when I was out there. This was many years ago. It was in 1994. I was there in 2002, just before I completed my PhD. But let's read this together. In an effort to curb certain diseases, especially AIDS, San Francisco has a program whereby drug users can exchange used needles for fresh ones. As reported in the Journal of American Medical Association back in 1994, go look it up. 1975 of the 5,644 intravenous drug users that were randomly sampled in San Francisco admitted to sharing needles. Is this sufficient evidence to say that the rate of sharing needles has dropped from the pre-needle exchange of 66%, test at the 0.05 level? So apparently what happened here is back way before 1994, there was a study done that found that 66% of drug users were sharing needles. Now, the obvious choice here, or I'm sorry, the obvious source of discussion or dilemma or I guess controversy is that should you give drug users free needles in exchange for the old ones that have been used? So there's little places set up in San Francisco where these drug users can go and properly dispose of the needles they've been using, and then the government gives them new needles so they can go out and continue using drugs. So I think the controversy is clear. I have strong feelings about this one. I'm not going to let you know. I'll let you figure that out on your own. Talk to your parents, talk to your friends, talk to your pastor, talk to whoever. But anyway, I'd say most people have really strong feelings on it, and I kind of do too. I'm just not going to tell you what it is. All right, what type of test should you use? Well, guys, this is a clearly about a percentage, so it's a 1 prop C test. Same things apply here. We want to see if the prenatal exchange has dropped. So this clearly going to be here, okay? Find and interpret the values for the appropriate test statistic, because I'm going to use the calculator here. So I am testing what, 66% from a sample that has 1975 out of 5644 total sample. We want to see if it's dropped, and we calculate. Wow. Well, it's definitely dropped. Well, that's kind of crazy. Okay. Our p-hat here is 0.34, so this is 35%. So 35% of those sampled, which is a significant drop from 66%, and it turns out that this drop is statistically significant. Anytime our p-value is less than 0.05, we get what's called statistical significance, sufficient evidence to indicate that whatever we're testing in the alternative hypothesis has happened. So we'll talk about that in just a second. So this is kind of an interesting situation where our test statistic, let me make sure you know which one is which, is negative 49.17. And our p-value is just 0. It's not really 0, but based on the rounding rules that your calculator uses, it gave up and just decided to call it 0. So what is your decision? Well, you tell me. Our p-value is 0. Our alpha is 0.05, clearly less. So gang, we're going to reject without question the null hypothesis. So a good way of doing that is get all dramatic and go all crazy and draw lines through it and everything else. So is there sufficient evidence to conclude that the prenatal exchange rate of 66% has dropped? Absolutely. Now, what's it dropped to? Well, that's where we'd use our confidence interval. So we go over here to test. Instead of using 1 prop z test, we'd use 1 prop z interval. So there it is. It knew you were coming. 1975 out of 560, 5644, 95% confidence level. So it looks like 33.7% to 36.2%. So it looks like it wouldn't be far off to say that that this program has almost cut in half the percentage of intravenous drug users who are admitted to sharing needles. So the program has clearly been successful. And you know, if you're going to get a grant and show that the progress and show the effectiveness of the program, this is the kind of stuff you'd have to show. You'd have to show p-values and test statistics, and you'd also have to get in some other things that we don't cover here. So guys, in this problem here, we would say that there is sufficient evidence to indicate that the prenatal exchange rate has decreased. All right, guys, that is it. Let me show you a problem that shows up on every final exam. So I would say something like this. How would I put it? You'd like to test at 0.05. All the info you have is the 95% confidence interval is 102.5 to 107.8. What's your correct decision? I would have the problem, these choices. Fail to reject H sub O. Reject H sub O and conclude mu is higher than 100. Reject H sub O. Conclude mu is less than 100. No decision can be made without the p-value. All right, you're looking at those three choices. What can we discard? Well, guys, we can definitely discard this one. We just made a decision earlier on without a p-value. It's called the critical value approach. That's not true. So what do you think? This 95% confidence interval tells us the interpretation, there's a 0.95 probability that mu is contained in that interval. Actually, technically correct, we would say there's a 0.95 probability this interval contains mu. The value we're testing, is it in that interval? It's not. So logic should tell you that if this value isn't in the interval that we have a 0.95 confidence in containing mu, then we should know that fail to reject isn't an option. Fail to reject would mean we're buying into that statement. We believe mu is 100, but how can we believe mu is 100 when it's not contained in our confidence interval that has a 0.95 probability of containing it? So it's going to be reject H sub O, conclude higher or lower, and I think this is the easiest, but since our entire interval is above 100, then it would not make any sense to conclude that the mean is less than 100. So guys, the correct answer here would be B. Gang, have a good one. I'm done.